project proposals are due this coming Monday, and there will be a Google form for submitting those, and the link will be sent out on Piazza. Yeah, we'll get started in a few minutes. You want to put this on? Sure.
Hi everyone, thanks for being here. Today it's our great pleasure and honor to have Mike Lewis from Facebook AI Research Fair to be our guest speaker today. And today he'll talk about deal of no deal, end-to-end learning of negotiation dialogues. So Mike has done a lot of great research in the area of NLP. And yeah, so it's great to have him today.
Great, thank you very much for the introduction, Don. Can everyone hear me okay? Cool. So yeah, I'm at Fair in Menlo Park on the other side of the bay. This will be joint work I'm presenting with Dennis Uratz, Jan Dauphin, Davy Parikh, and Dhruv Batra at Fair. So in this work, we're going to be working on trying to train chatbots that can negotiate with people in natural language. Before we get on to stuff I actually want to talk about, I just want to quickly get this out of the way. So I don't know if some of you saw last summer, there was a few days when there were some headlines like this in the press, where things like, this one's like, machines taking over, RoboStop, Facebook shuts off robots after they chat in secret code. This made headlines around the world, apparently. Looking inside, we can see apparently the incident resembles the plot of the Terminator movie, in which a robot becomes self-aware and starts waging a war on humans. If you saw this, I'm sorry to disappoint, but we will not have any self-aware robots, and it's probably going to be less exciting than the Terminator. But yeah, basically this came out of an attempt to talk to the press about our work and be honest about the fact we had some failure cases and not everything worked first try. Unfortunately, the press interpreted things not working first try as us losing control of our AI systems, and then the fact we, I don't know if there's some hyperparameter searches and not all of the things lived, they took as us shutting down these dangerous experiments. Yeah. Okay, so stuff I actually want to talk about. So in this work, we're going to be training bots to hold negotiations with people. So negotiation hasn't actually seen a lot of work in the AI community, and so I'm just going to spend a few minutes trying to motivate why I think this is a really interesting and important task to work on. Okay, so first of all, why are we doing negotiation? Negotiation is actually pretty useful, I think, in general. When we got multiple agents who have different goals, and not all of the goals can be achieved at once, so they need to come to some kind of compromise. I don't argue this basically happens all the time. I mean, we do this all the time without thinking about it, whether it's like agreeing which TV channel to watch or where you should go out for dinner with your friends. Often people just have their own preferences and trying to find some mutually good solution. Also, it's kind of an interesting thing. So in AI at the moment, we've got lots of people work on kind of zero-sum adversarial games like chess and Go and StarCraft or whatever. And also a lot of work kind of assumes like fully cooperative settings where the AI system is basically kind of a slave to people and just trying to do whatever people want. But really there's kind of all this space in the middle where games are like not zero-sum, but there's people are coming to the game with their own goals. They're not trying to defeat the other person or fully serve them. They're just trying to like find a good solution that works for everyone. It's also quite an interesting problem to study from the NLP point of view. There's kind of like a linguistic and a reasoning problem. So we've got, right now we can build things which can use language fairly well in kind of word matching settings. So things like machine translation, where you don't have to be particularly creative about what you say. You just need to kind of transfer language from one language into another. But in negotiation, it's more than that. You need to actually have kind of reasoning steps where you need to actually think intelligently about what to say and act strategically. To do this, you have to like do things we're bad at in NLP. So you got to like interpret multiple sentences of context and as well as your own goals, and then use this to formulate some new message. And you got the, if you look at good people at this, they use all sorts of tactics like kind of making proposals and counter-offers. Sometimes they're deliberately vague. Sometimes they actually try to deceive the other person or bluff with them. And often in the end, you have to do some kind of compromising step. And all these things are pretty difficult for current models. You can't just do this with simple word matching techniques. It's also a pretty hard problem. I mean, lots of goal-oriented dialogue settings actually do have like some fairly trivial rule-based solutions, particularly if the agent can just simply transfer all the information it has to the person and let the person actually do the hard work. These tactics don't work at all in negotiation. So there's actually an incentive for our agents to try and withhold information. If I'm negotiating with you and I just like tell you everything about what I want precisely, then you can like probably craft some kind of arrangement which gets you everything you want whilst not giving me very much. And it's also kind of a problem that's pretty difficult to solve. So I mean, you can always like negotiate with someone smarter and better, and then that means you have to maybe use different tactics or learn to think harder about things. But finally, it's quite a convenient task. So we can evaluate performance on this pretty well. I mean, we can just hold negotiations and see how good an outcome our systems get. And if we want to do development for this, we can just have these agents play each other in self-play. Okay, so I think, yeah, to summarize, I think negotiation is, oh sorry, one other thing. I think this problem does actually have some real applications too. I certainly don't want to say that like these bots are going to be like doing Brexit negotiations or like solving the Middle East peace crisis, but I think there are some use cases for this. So I mean, many people actually have to do negotiations when they're applying for new jobs, and lots of people don't have much practice with this, and like sort of culturally find it like very hard and awkward to do this thing of like asking for more. I think it's the kind of thing where perhaps if people actually had automated systems they could negotiate with, then that would remove a lot of the awkwardness and really help people do this better. Okay. Oh, I meant to say at the start that if you've got any questions about any of this as we go, then feel free to jump in with questions as we go. Okay, so there hasn't been a lot of work on this task before. So first of all, we set out to gather a data set of how people actually negotiate so we can start training models on this. We've got kind of a high-level framework here where basically we've got two agents. We're going to initially give each of them some kind of goals, some kind of value function that tells them what's a good outcome for the agent, what's not a good outcome for the agent. And we're going to make it so that these agents can't see each other's value functions. So if I'm negotiating with you, then I don't know what you want, you don't know what I want. So which forces us to use communication, natural language to actually work this out. So then these agents basically sequentially exchange natural language messages with each other. And at some point, you can enter that we've made an agreement. After someone says we've made an agreement, then both agents are going to independently select what they think we actually agreed on. And again, we're going to make it so they don't get to look at each other's output there, so they actually have to have agreed in the natural language what this was. And finally, if they both select the same agreement, then they'll get a reward according to the goal function we gave them initially. If they disagree, then we can say both of them get a 0 reward. So any agreement is better than no agreement. Okay, more concretely, we had a simple setup of this, where basically we show two agents same set of objects, but we give each of them some value. So basically there's like a group of objects on the table. You got to agree how you're going to divide these objects between you. We had a pretty simple domain. We had some certain number of books and hats and basketballs. And then we give some scores for each of these to each of the agents. So the agent on the left particularly likes the basketball, the agent on the right particularly likes the hats. And then they've got to come to some agreement on how they're going to divide these up. So in these kind of setups, there's like multiple good solutions. So for example, they might come to agreement here, where like the agent on the right gets all the hats that he wants, and the guy on the left gets the rest. And then the guy on the right will get 9 points, the guy on the left will get 7. Or we can maybe divide it up like this, where in this setup, the agent on the left is going to get 8 points, and the agent on the right will get 6. And both these are pretty like reasonable outcomes, and like which of these outcomes they'll go for depends on how good these agents are at negotiating. Okay, so yeah, here's an example dialogue we had. Example of this going, so we give the agents these value functions, we let them have this dialogue here where they come to some agreement, they both enter which items they think they're going to get, and then they get some points. So we set this up on Mechanical Turk. We basically paid people to play this game with each other. Has this fairly simple interface here. And we actually, when we did this, we got some pretty interesting dialogue. So here's an example dialogue from our data set. So the first Turk said, like, you can have 3 books, I'll take the rest. The other makes a counteroffer, a basketball and a book. The agent left now makes a compromise, and instead of offering 3 books, offers 4, saying a final offer. The agent on the right did not like this and says, that deal is not fair, I will not accept, split it down the middle or no deal. So threatening to sort of walk away. So walking away is worth like minimal points to both agents, but we often found they still sort of threatened to do this anyway. The agent on the left kind of calls a bluff, it's like, fine, walk away with nothing. Agent right's like, you're doing the same, hope you enjoy your rejection. The agent left has his bluff called, he's like, fine, I'll compromise, I'll take that. And the agent on the right's like, awesome, pleasure doing business with you. So these dialogues are pretty fun and interesting. So what we basically want is to have bots that can actually do this kind of thing, like sort of make offers, make counter offers, sort of bluff as long as they can get away with this, and then finally make a compromise. Cool. So we gathered the data set. We had about I think 6,000 dialogues. It takes kind of an average score of about 6 points out of 10, and they were able to like come to some agreement in about 80% of the cases. Okay, so next up, we're going to describe how we can train some models to do this task. All right, so to quickly going to talk about stuff we're not doing. So traditional dialogue models kind of relies extensively on having annotated state representations. So like, say you got some restaurant booking system, like the guy goes, I want to book a burger restaurant, that gets transferred into some kind of like logical representation, like inform that you want a particular food type. And that's used to like update some kind of state representation that like kind of keeps track of what things the person wants. And then based on the state representation, the system can like generate some new logical form what it wants to do, like query the price, and then generate out a message. And this carries on like this. All right. So this kind of approach has got a lot going for it, in that like it makes this really nice, clean separation between like problems of like interpreting the message you've read, kind of doing some reasoning about the message you've read in the context of the state you're in at the moment, and then generating some new message to fit that context. And this is like a really nice, clean factorization of the dialogue problem into interpretation, generation, and reasoning. The reason we don't want to go this way is it kind of assumes you've got these annotated dialogue states. So you have to get these dialogues, and someone has to sit down and write some logical forms that like express what's actually going on here and what these messages mean. And maybe that's an okay thing to do in some domains, but like really I think this is not going to be like the ultimate scalable solution to this problem. I mean, firstly, like, there's been like huge amounts of work on trying to like annotate natural language with logical forms in a way that like fully captures its meaning. And it turns out it's really, really hard, if not impossible. And generally, if we can like build like kind of soft, latent, learnable representations, that often tends to work out well. And also, even if you annotate these representations for your domain, then probably you can't use these representations in other domains. Okay, so instead we're going to take a different approach. We're basically going to have like an end-to-end model where essentially we're going to take some words in, throw it into some kind of recurrent neural network or something, and have this recurrent neural network spit out replies word by word. So this makes the problem a lot harder because you can't get away with like rule-based generation now. And you also can't use symbolic reasoning, which means reasoning has to be done in some kind of way that's more compatible with neural nets, which is challenging. Okay, so we're going to have a single model that's going to try and do interpretation, generation, and reasoning, all in its latent states. We're going to learn a representation dialog state. A plus point of this is we're going to get pretty cheap data collection, so we don't have to pay anyone to sit down and annotate our dialogues with what's going on. We're just going to have people talk and try and learn directly from observations. And also, if we want to multitask this with other tasks, then it's much easier with this kind of approach. But really, kind of the crux of what we're trying to get at in this work is like, if you just like take an end-to-end neural network, can it actually learn to reason? So, sure.
Can you say what you mean by easy multitasking?
Oh, sure, yeah. So basically, all I mean is if you were to get a data set for this domain, and say you're going to like have some completely other tasks that you trained you got some circuits doing something else with dialogues, you could train the same model on both of these, and in principle, it shouldn't get any worse on either task. I might even be able to learn some things from one task that transfer to another. In contrast with like traditional kind of dialogue models where you've got these annotated states, then there's not really a way to do that so well, because probably your state representations will look quite different in different domains. Any other questions so far? Cool. Yeah, so like kind of like the crux of what we're trying to get after here is like, I mean, it's pretty easy to make neural nets will like spit out plausible looking sentences in this kind of context and like propose different deals or agree to things or whatever. But what we want to do is can we actually learn to reason? So can they learn to say things that are more than just like plausible English, but actually things which are intelligent in the situation and are going to help the agent try and achieve its goals? Okay, so first of all I'm going to describe a baseline model. This is a really, really simple model. It's actually so simple I'm not sure anyone's done this before. But basically we're going to take our input dialog, which is like, I don't know, some messages said by two different agents. And then we're just going to like turn this dialog into a linear stream of tokens. So these tokens basically contain the messages sent by the two agents, interleaved with these like special read and write tokens, which just denote whether we're saying this message or listening to it. Then we're just going to like train a simple conditional language model on this. So it's basically a sequence model that like reads in the value function we have on the left and tries to predict the dialogue here. So just word by word, it's going to try and predict each word in this dialogue. And finally, we're going to train some additional classifier at the end to try and predict what the deal is. I don't want to talk too much about this extra classifier. It turns out this problem of like working out from a longish dialogue exactly what they agreed on is not trivial, but again, it comes down to basically a sequence model. So if we train that dialogue, we actually do this twice. So basically, we split it into two dialogues, one from each user's perspective. So these these perspectives differ on like what the input goals were on the left, so like what the values the agent was after, and they differ on these read and write tokens, so just inverting those. Okay. And then we can simply train this model to just try and maximize the likelihood of human dialogues. And we can simply decode this by just sampling messages. So every time step, you basically just have a distribution over words, and we'll sample one of those. This is a very simple, easy, efficient model to train. And I'll show later on that it's actually quite convenient for doing forward modeling with. Okay, so this model kind of works, but it's got some issues. So it turns out to be a very friendly negotiator. So you get dialogues where the person says you can have 2 hats, and the bot's like, thanks, deal. You say you can have 1 hat, and it's like, great, thanks. You say like, I'll take everything, and the bot's like, sounds good to me. This actually happens, right? The bot is like, this problem is totally not unique to our setting here. So people notice in lots of different domains, particularly dialogue domains, that these neural nets are very prone to like saying like the most generic, simple thing, which is like valid in pretty much any situation, but like maybe not the smartest thing to do. So it's kind of like this complex multimodal distribution. They just try and learn the easiest thing, which is just to say some words which are always a good idea. Well, always English, but like maybe not always the smartest thing to do. Yeah, people notice this in lots of other tasks. So what's wrong with this model? Why is this happening? I think really the problem here is this model like isn't really intelligent. What it's trying to do, it doesn't know anything about what it's trying to do. All this model knows how to do is like say, I don't know, in this situation, try and guess what the next word a person would say is. It doesn't know anything about its goals, it doesn't know anything about the outcome of the task. And that means that it ends up just agreeing to things very easily, and it can never really go beyond people. Like the best case scenario is it matches like the average human negotiator, but really we want models that can actually learn to be smarter than people.
Do you think so here it looks like it's doing worse than a lot of human strategies, right?
Yeah.
Do you think the baseline could be improved a lot by if you fed in as an additional feature like the number of points that it's getting if it stops the dialogue right there?
Sure. So that's an interesting point. Firstly, that's like slightly tricky to do because we don't actually know. Yeah. We don't have like annotations on what the deal is at the moment.
It'd be a separate neural net too.
Yeah, so we could try and do some kind of like Q-learning or something to try and learn the expected outcome at this point. Yeah.
Well, how would you add like that into the likelihood? Like we try and match the likelihood that the agent that the human got?
Or I was thinking of using that as a feature to predict the next tokens or the next human tokens.
Well, it's a bit tricky to see how this works. So I mean, at the start of your turn, you could like guess how many points are available now, and you can imagine that if it's like a low number of points, then maybe that would push up the likelihood of saying something else that's like not agreeing. But yeah, I'll talk about a few approaches how we can improve over this baseline. Cool. Okay. All right, so yeah, if we want to go beyond this, so one approach is to try and do, rather than just training like to maximize likelihood of human dialogues, we like train the model to, with respect to goals somehow. So the simplest way to do this is basically have these bots like talk to each other. So we train them with a couple of bots, just have them have like thousands of dialogues with each other in self-play. And then at the end of this dialogue, like both these bots are going to get some kind of reward. So here the bot on the right is just like agreed to easily and got a low number of points. The bot on the right left as well and got some points. And then we can basically just like backpropagate these rewards using reinforce. So if you haven't seen reinforce, basically what it's going to try and do is learn actions which lead to higher rewards are going to get kind of more likelihood associated with them, and actions that led to low rewards will get downvoted. And we can do this many thousands of times. Unfortunately, if you just like do this naively, you end up like after enough dialogues, you end up having conversations like this, where so remarkably in these second dialogues, they actually do come to agreement. Like the bots do seem to know what they're doing, and like they will agree that this corresponds to someone getting like 2 hats in a book or something. But, unfortunately, for our goal is to have like bots that can negotiate with people. This isn't like super helpful for us. And basically what's happening is like our objective here like doesn't really, no longer contains any like information about like trying to act like humans. It's just trying to maximize the reward the bot gets. And it turns out just saying this random stuff can like help the bots get higher scores than they would do otherwise. It's almost like kind of constructing adversarial examples where you got bots like trained to maximize likelihood. It's never seen a sentence like this before, so it doesn't really know how to interpret it, and maybe like it somehow pressures the bot into just folding. Yeah.
So have the bots ever tried to exchange, say, telling each other what their reward functions are, and then try to work out the optimal solution? Has that ever happened?
I'm not sure. Honestly, they probably don't do anything that smart. I think, well, firstly, like there isn't really an optimal solution for both parties. Like, there's an optimal solution for each of you, but like, there's kind of this Pareto frontier where like if I can get more points, well, you get less, and if I just tell you everything about my reward function, then I'm not going to get like the best solution for me. So like just trading reward functions isn't a good strategy, and I don't think they'll learn to do that even if they were smart enough.
This was, I guess, the rogue secret robot code.
Yeah, yeah, it's pretty exciting. Yeah. Okay. Okay. So we can do something else instead. Basically, we can like, instead of just doing pure reinforcement learning, we can try and like interleave reinforcement learning with supervised learning. So basically, the reinforcement learning is trying to get as many points as possible, and supervised learning is trying to make the dialogues look kind of like what humans say. And if you like very carefully balance these two things, then you can keep it kind of improving its score while still looking at English. One challenge of this is you still end up with pretty aggressive negotiation bots. So this bot here on the right is like, these bots often have pretty long dialogues where like bot on the left's like you can have 2 hats, bots on the right it's like I want 3, the bot on the left's like you get 2, the bot on the right's like I can't agree, you get 3. The bot on the left's like you get 2, final offer. And they basically continue doing this all day. These bots are like very, very stubborn, patient negotiators. Basically, the bots learn the strategy of just like infinitely repeating demands until the other person cracks and gives them what they want. Which is one way to go. But okay. All right. So to summarize this goal-based training approach, we're going to have lots of dialogue and self-play, and then interleave reinforcement learning and supervised learning updates to try and balance human-like language with trying to achieve goals. Okay, but this was not a great success. It sort of helps a bit if you try really hard, but it's very difficult to get it working. Sensitive type parameters, maybe it's too aggressive at negotiating, and if you're not careful, it says things that people can't interpret. All right, so instead we're going to try a different approach here. So we're going to take some inspiration from Jan, who says that prediction is the essence of intelligence. I think what he means by this is like if we can like try and predict what's going to happen in the future. So like if we're smart, we can like I know how you're going to reply to what I'm saying, and I can like adjust my response to fit with that. I'll quickly show you what I mean by this. So basically, we're in some situation. The human said to us like, "You get 1 book, and I get the rest." So we'll like consider one thing we might say. We might say that's a great deal. And then we're going to do even more. We're going to like imagine how you might reply to this. So I have some like, Major has some mental model of how people act, and thinks people might say something like this. And at the end of this, we'll get some, we'll get 1 book, and we'll get a certain number of points for that. We can also like kind of sample other things the person might say, and we can also end up with the same number of points. But then we can also like maybe consider other options we could say. Maybe we don't have to agree. Like maybe we could say some other sentences which has lower likelihood under the model, but might be good. And then again, we'll just simulate out these dialogues and like see how many points we end up getting. And then at the end, we'll like kind of collapse all the points we got for the different options we could have taken, and get some average score. So this is like kind of a simple version, like kind of Monte Carlo tree search that things like AlphaGo are doing. And then simply, we're just going to take the sentence we can say that gets the highest reward for us. Right. So this is a very simple algorithm, which we call dialogue rollouts, where you just generate a candidate set of things to say. Have thousands of simulations of how the dialogue might go after saying this. And then just take the sentence and maximize your reward. So this is pretty nice because, like, firstly, we don't actually do any training, additional training at all for this. Basically, simple recurrent neural net we described before. You can just basically keep on sampling beyond the end of your turn, and then you can work out what future turns might look like. It kind of gives the models kind of like ability to understand the consequences of reaction. So when it says something, it has something in mind about how the dialogue is going to go after this, and what kind of situations it might lead to. Also, at least in principle, it gives the model to kind of go beyond what humans are doing, so the model can actually potentially learn tactics which people don't have. And yeah, it's very easy to implement this. And in contrast to reinforcement learning, this basically worked straight away, whereas reinforcement learning took lots of time tuning hyperparameters.
Question.
Yeah.
So here, the expected reward is assuming that all branches after the decision you're making right now are equally likely? Is that, or the probabilities given by your language model?
Exactly, the probabilities of the language model, yeah.
As opposed to assuming like a more Monte Carlo tree search type thing where the other person does the same thing.
Yeah. So absolutely, it's a great question. We could totally like branch again after each of these steps and do a tree search. There's a few reasons we didn't do that. Firstly, so in cases where that kind of approach works, things like Go, there's like a pretty limited number of moves, like is it 400 in Go or something. Whereas here, I suppose, is like the number of English sentences. So we need to have some kind of like other way of pruning these down to like a reasonable set of things, and we're never going to like do a tree search of a reasonable proportion of the space. So we just like prune it pretty early, just like branch twice, and then just assume everything's equally likely after that. But great question. Cool. Okay, cool. So there's the models I want to talk about for this. Let's see how they do. So the models, I'm going to be comparing what's called a likelihood model, which is basically you train it to maximize the likelihood of human dialogues, and then also decode it to just say the most likely thing a person might have said. Reinforcement learning basically takes a pre-trained model and fine-tunes it with a combination of supervised and reinforcement learning. Then we'll have like a rollouts model where we just take the simple supervised model and try and decode it instead of maximizing likelihood to maximize reward through these rollouts. And finally, a combination of reinforcement learning and rollouts. Okay, so if we just evaluate how these agents do in dialogues, then this is these are dialogues against the likelihood agent I split. So our simplest model is doing self-play with other models. I broke this out into scores on just a case where they actually were able to come to some agreement, and scores on cases where they didn't agree. And it's a fairly clear trend that basically the likelihood model does least well. You get improvements from both doing rollouts, doing reinforcement learning, and at least in these experiments, the improvement seems to be kind of additive, where if you combine reinforcement learning with rollouts, then you get a bigger improvement. We can also look at the kind of the relative score they get. So this is like how much better it does than the opposing model. We didn't really train it to do this. We just trained it to maximize its own score rather than do better than its opponent. But again, we see a similar trend where reinforcement learning and rollouts are both useful. We also see that they are able to agree more, and they lead to a kind of more Pareto optimal solutions. So Pareto optimal solutions are ones where one agent can't improve its score without worsening the other agent's score. Unfortunately, if we look at dialogues with humans, then the picture's kind of different. Firstly, scores are uniformly a bunch lower when we do this with humans. So basically, we just put these agents on Mechanical Turk and ask them to talk to people. And here we see that actually, in terms of the most relevant score is the score on the left, which is where the score the agent achieved. And we see here that using rollouts does improve the score, but actually reinforcement learning doesn't really. The graph on the right kind of gives a reason why, where basically reinforcement learning works great in cases where the bots actually agreed with where the bots agree with people at the end, or they're able to come to some compromise. But often people are just prepared to walk away from people. The reinforcement learning, either like the language wasn't good enough for people to understand and it led to confusion and disagreements, or people just got so frustrated with arguing with the bot that was just so stubborn they were prepared to walk away with no points rather than actually just compromise to this bot that would never compromise with them. Yeah. And again, if you look at the agreement rates these bots reach, then rollouts does a fairly good job, but like when you combine reinforcement learning, that really lowers the agreement rates. Okay, so next, a bit of analysis on this. So this is a good example. This is a conversation that a human had with one of our bots, where the person says it wants a book and hats. The bot makes some counteroffer. The person compromises a bit. The bot then comes up with this long sentence. I can't make that deal. I need the ball and the book. You can have the hats. There's actually quite a good sentence for bot to come up with, given this doesn't actually carry in its training data. The person threatens to walk away, and our bot suddenly, when it sees the person threatening to walk away, suddenly backs off and decides to compromise a bunch and offers the person what it wants. The person threatens it again. And finally, the bot compromises the third time and gets the deal. So this is kind of interesting just because it shows the bot at least seems to be able to pick up the fact that there's a risk of getting no points if the human carries out its threats and learns to make counteroffers until the person will agree with it. Also, this kind of looks like a real dialogue. I mean, this is dialogue two people could have had, and the bot does a pretty good job of impersonating human dialogue here, as well as coming up with new sentences which didn't occur in its training data to meet these new situations it finds itself in. Cool. Another interesting thing we noticed was we noticed quite a few times this bot using this tactic where it seems almost like it's trying to be deliberately deceptive. So often the bot's in a situation where maybe there's one item that's worth something to it, the basketball, and there's a bunch of other things it doesn't care about. And the bot starts out with saying it wants the basketball and the two hats, even though it really doesn't care about these hats. A person's like, it wants at least the book and 3 hats. And the bot's like, fine, okay, deal, I'll take the basketball and 1 hat. And this is great for the bot because it walks away with the full points, but the person also seems happy because the person saw the bot seem to be prepared to compromise, and it seems like a reasonable, if you don't know what the bot's value function is, then it seems like the bot is actually trying to compromise with you and be a reasonable negotiator. Unfortunately, the bot also learned some pretty bad tactics, particularly when we use reinforcement learning. Here, the person makes an offer. The bot's like, okay, you get offers the book. The bot's like, okay, you get the book and I get the rest. And the person's like, no, no, no. I said, I'll give you the book and I'll take the rest. So what the bot seems to be doing is maybe, I think it learned that if it starts things by saying okay, then that's more likely to be followed by an agreement, just because there's this correlation data when people say okay, deal, that leads to an agreement immediately after. The bot's kind of misunderstanding the correlation and causation here, where people tend to only say that in situations where the deal was agreed. Instead, it thinks it can just force someone to agree by just starting out by saying okay. Also, these bots, particularly when you do reinforcement learning, they get they're really aggressive negotiators. So, the person makes an offer, the bot says it wants basketballs and the hats. The person makes a counter offer, the bot says it wants the basketballs and the hat. The person's like, can you read what I'm saying? I need 2 balls in the book. The bot's like, I'll take the balls and the hat. The person's like, fine, no deal, whatever. The bot's like, and maybe this was effective in its reinforcement learning self-play dialogues where the 2 bots were happy to do this kind of thing until one of them cracked, but it does not work so well in Mechanical Turk because we got some angry emails about this. Okay, cool. So to wrap up this part of the talk, I tried to argue that negotiations in natural language are actually a really hard and interesting problem because they combine these kind of reasoning skills with the ability to communicate in natural language, trying to make bots that can do both well is pretty challenging. I think kind of like the main technical contribution that came out of this is that this approach to doing planning using rollouts is actually very effective and for us worked a lot better than reinforcement learning. I've got some more stuff to go over, but have you guys got any questions?
Yeah, when I was reading the paper, I was really, I noticed that we described collecting the data set of mechanical turk, that the way you paid the, the data set providers, generators, was like some money for each dialogue and then like a bonus if you got 10 points. So that's like a very different reward function than what the reinforcement learning is. So can you talk about if that makes any if that was like sort of any problems?
Yeah, so I mean, that's a great point. So firstly, we didn't actually tell the Turkers what, we just told them to get rewards if they did well in the negotiations, so they didn't quite know exactly what they were getting rewarded for, which helped a bit. So there was kind of gave us some incentive just to try and do well rather than hit exactly 10 points. I mean, the real problem here is that these Turkers actually have a very different, very complex value function, where really what they're trying to optimize is kind of, I don't know,
money per time.
They're trying to optimize money per time, and maybe like if it's an entertaining task to do, then they're happy doing it longer than if it's a boring task. And so that means that like, for example, the Turk's quite happy to just like stop a task if it looks like the person negotiating with isn't going to give them a fair deal in the end, so they can like go on to someone else where they can actually do better.
That's what I was looking at, the the huge plunge in like deal agreement rates, when they go up against.
Yeah, exactly. Yeah, people were just realizing that like when they talk to these bots, then it just wasn't worth their while, and they negotiated so hard that it just wasn't worth trying to actually come to a deal. They should just like run off and like try and find someone else to talk to who might give them a better deal. So we're doing all these experiments simultaneously, and there's also this like purely likelihood bottom, which sort of paid out money a lot faster because it would agree with them. So yeah, basically the problem is that, as you say, the rewards that the Turker are optimizing are like very different than the ones the bots are doing. This was the best compromise we could have. I don't really know how we could have made these rewards more in alignment, but yeah, it's something to think about. Yeah?
I have two.
Sure.
So first, earlier part of the talk, you laid down the question whether the bots will learn reasoning from this dialogue.
Yeah.
So it would be nice to hear, after this, what your thoughts are. And also too, when you look at the bots dialogue, I mean, is a bot like in some sense consistent? Meaning, like once they negotiate to a certain stage, like will it actually say things that actually make sense, or it actually won't?
So the first step, the answer is like a very, very, I think, small step in that direction. So, I mean, in terms of reasoning, they at least learned that like just agreeing all the time is not a good tactic, which I mean is kind of obvious, but like the vanilla neural nets just didn't pick this up at all. And they seem to learn that like in good examples, they seem to have this kind of behavior where they kind of sort of progressively compromise a bit, but it's less clear they're doing this. I mean, these agents still have a very flimsy idea of like what they're saying actually means. They so they just see this sequence of tokens. They don't seem to very well be able to ground it out into like knowing exactly how that corresponds to particular deals they're offering. So I think, yeah, this kind of planning using rollouts does give some limited ability to reason, but it's definitely some way off what humans are doing. Did that answer your question?
And then about the consistency, so basically.
Yeah, it's mostly fairly inconsistent, to be honest. You can like definitely find examples where it seems to be kind of start out with something, then consistently sort of back down from that, but it's probably just like being too optimistic looking at data. A lot of the time it seems to kind of jump around quite a lot, make one offer, then make another quite different offer. I mean, so some of the consistency comes through like the fact it's got the same value function at each time step that it's trying to optimize, so that kind of naturally leads it towards doing the same kind of things. but I'm not sure how much it shows as like kind of a long-term plan of actually, would lead to it being really consistent.
Do you try to have the bot also predict the value function of the other bot?
We did experiment with that. We couldn't make it work, unfortunately. It seems like it should be a really nice idea where if you like, you can train a classifier that each time step you predict what the other person might have, then you condition on that while you're generating your text. It never worked for us. I think a lot of the time it's quite hard to guess what the other person's value function is, and also there's like, even given that, there's a huge amount of variance in what people actually did given a value function. So maybe with like a different task or more training data, this would work, but we were never able to get.
During human negotiation, the humans would try to do that.
Oh, absolutely, yeah. So people kind of have like a theory of mind or something where they're trying to see how people are acting, trying to predict what they're doing based on that. But we were never able to get at least. I mean, maybe the networks are implicitly working these things out based on trying to predict what people are saying. That gives them some kind of, I guess, implicit guess at what the opponent's value function is, but we were never able to get an explicit reasoning step to actually outperform that.
When you had, I guess the way you structured the dialogue is, just being like a string of tokens. Is that, do you think, generalizable to like a three-part negotiation, or do you have any, I guess, like intuition on whether it should be or wouldn't be?
Yeah. So I mean, in principle, I guess you could like change these read and writes to like agent 1 says, agent 2 says.
Yeah.
I think that would be fine. I think three-part things gets a bit complicated when people like start talking over each other, or like it's not clear what ordering people should get to speak in, which is why we just kept to this simple case. But I mean, at least in principle, sure. Cool.
You showed a plot where you showed how well the different approaches did against the supervised baseline. I would sort of, given that the supervised baseline doesn't really know what it's doing, I would sort of expect there to be some kind of adversarial example that just causes the supervised baseline to just give you everything. Do you think that's the case? And I mean, it seems like you'd have to think about adversarial examples.
Yeah.
Deploy something like
I think like actually a lot of like reinforcement learning was finding this kind of thing. So it kind of learned that if you show the supervised agent some like string of words which it's never seen before, it's never trained on this, who knows what it will do. Maybe there's some of these like press and buttons inside that cause it to just say, yeah, you take everything. I think that's a lot of what we saw in this kind of inventing its own language thing, with the bots just learning how to create adversarial examples for each other, which, is like, I guess, kind of clever, but also really not what we wanted to learn.
One other
Sure.
question is just to get the language to look more human-like, like real language, you interleave the supervised training. Do you have thoughts about how that would compare to sort of like training a discriminator or trying to fool a discriminator?
Yeah, that's a great question. I mean, and sometimes it would probably look kind of similar in the end in terms of the updates you were doing. I mean, that would definitely be another way you could do it. We haven't tried it yet, but I think, it's adversarial training type approaches where trying to predict what sentence spoken by human or bot would be a good way to go. Cool. Any other questions on this? How long have we got? Is it cool?
We have room until 2:30.
Okay, cool. I'm just going to quickly go over some like follow-up work we did on this then. This is going to be very brief. All right, we call this like hierarchical text generation planning for this task. All right, so in this talk we're talking a lot about like trying to sort of how you got these reasoning steps, you got these kind of linguistic steps. And I think one of the real problems, one thing that caused a lot of problems we've been seeing is you kind of get these sort of entangled representations. So the RNN is just learning these like vectors each time step. And these vectors have got to like kind of contain information about both like what plausible words are and like maybe some idea of what the plan is, but they don't really disentangle these at all. So here are two sentences the bot could say, where like, I know, I'll take the hats of the books and you take the hats of the books. And these sentences seem like really, really similar. And if you're trying to train any kind of neural net on these, it will think these sentences are very similar, like the first tokens followed by the same words in each case. But these really, in the context of our dialogue, they mean totally different things. Like if you say one, you might get lots of points. If you say the other, you might get no points. So this difference, the fact that these sentences are similar doesn't mean they're both equally good. Alternatively, you could say something like, I want the basketball, you get the rest, and in the context of dividing up these items, that sentence means the same thing as the one above it, but like, even though the words are completely different. So the fact that the words are similar like, doesn't really tell us anything at all about whether these sentences actually mean the same thing at all. And it's like really, really hard for these models to pick up on this. And I think this problem actually causes a lot of the issues we've had with these models. So for example, in dialogue rollouts, it sounds like great in principle, but what often happens is you say something like, so the human says something, and then we generate a set of candidates. But often these candidates actually end up all being the same thing. They're all like just paraphrases of each other, where they're all like just different ways of making agreement. So although these are like, there's very little word overlap here, the semantic overlap is actually very high. And then we can roll all these guys out to the end of the dialogue. We basically get the same deal and the same points in each case. And we just learn that like we have no options. So the rollouts actually aren't buying us anything at all here. We're just saying the most likely thing. And again, this kind of comes up in the reinforcement learning too, where like what we'd really like our reinforcement learning to do is be able to like kind of keep on human language, but like sort of affect some kind of higher level strategic decision making. But what happens is because we've got these kind of entangled representations, these vectors are containing information about both what we're saying and how we're saying it, then when we backpropagate these rewards, we end up like just breaking the quality of the language rather than actually like without sort of learning anything smart to say. Okay, so I'm going to describe a quick model for how we can try and fix this. So our current model setup looks something like this, where I basically have a little RNN that's predicting words at each time step. The first step we're going to do is like switch this into like a hierarchical RNN. So this RNN is going to, as well as the one we described before, we're going to have a kind of higher level one, which is basically just reading in one message at a time. Well, this is really easy to implement. You just like take the final hidden state at each turn or something and feed this into this other RNN, and then you use that when you're generating the next turn. And this kind of has the advantage that like really shortens the dependencies between turns. So I can like, it makes it much easier for the model to see what you said 3 turns ago than having to remember through all the words in between. Right, that still doesn't solve the problem. What actually we're going to do is going to adapt this model some more and introduce some kind of latent variable into the RNN. So here we've got this latent variable called Z in this little yellow circle. And it's going to sit in between the hidden state of the RNN and the words it's going to generate. And this is going to be, we'll assume this be just some discrete latent variable for simplicity. And ideally, this variable is going to kind of capture the underlying meaning behind the message we're about to generate. So we kind of think about the Z as being some kind of like plan for the message. So what we'll do is when we want to generate a message, we're going to first of all sample this latent variable Z, which will kind of tell us something about the meaning of the message. And then we're going to generate text based on that. And it's kind of like sort of factorize our problem back again into like separate problems for generating text and separate problems for planning what we want to say, which I think is a good thing. The question is like, but how do we learn this latent variable Z that actually captures what messages mean? So there being kind of a few models that look a bit like this, through like Sean Wen at Cambridge, where they basically just like train this kind of setup end to end. So you train your Z by a Gumbel softmax or whatever else to learn to maximize the likelihood of the dialogue. So we're trying to learn Z that was going to be like informative for predicting the next words. It turns out this, in our setting at least, this really doesn't work well. Basically, if you do that, you'll end up with like one value of Z, which gets these top 2 messages in the same cluster because they got very similar words, and like this is very informative for predicting this next message. Even if this third message means the same thing as one of the other ones, the words look so different that it just gets assigned to a different cluster. And this is not what we want. We want the plans that capture the meaning of the sentence, not actually what the words are. So instead, we're going to go with a different approach. We're going to do a pre-training step where basically we learn to cluster messages based on their meaning, and then we're going to retrain the model using these latent representations instead. Kind of the intuition here is we want to kind of capture the effect that a message has on the continuation of the dialogue, rather than what the words in it are. So we're going to for doing the pre-training clustering, we're going to set the model slightly differently. So here, basically, whenever we read in a message, it's going to be encoded into a latent variable z, and then fed into. We're just going to feed in z into the RNN over messages. And this means that whenever we're generating words from this model, it's never actually seen the words in the previous bit of the dialogue at all directly. All it's seen is what they've been sort of compressed through this discrete bottleneck z. And that means that if the model is going to learn to predict the rest of the dialogue accurately, then it really needs to learn z's which actually capture how z is affecting the dialogue, and not just the words in the message. Also, to improve it slightly better, we're going to have a step where we also, at every time step, try and predict what the deal is at this state. So basically, to do this, we took our classifier for predicting from a dialogue what the deal is and ran it in intermediate time steps. And that gives us a distribution over what deals might be agreed at this point. And then we try and just optimize KL divergence to that as well. So again, this is forcing the model, it's got to really try and extract the meaning of these messages into this variable z, or else it can't learn anything. Yeah, I don't have time to explain exactly how we're training this, but basically we do EM, and there's details in the paper. So now we basically learned for all our training dialogue, all the messages in training dialogue are assigned to some message set. And these kind of learn much more semantically coherent clusters where it doesn't really matter what words people say. If it's expressing the same deal or the same kind of sentiment, then they end up in the same cluster. Then using these, we're going to retrain our model. So now we've got kind of gold standard clusterings for each of the training messages. And what we're going to do is train a model such that using these. So to do this, now Z is very informative about what the meaning of the next message is, but we need to still train a model for how you translate that message, latent representation, into a good message. And we also need to learn how to predict what plan or what latent variable we should choose at a given time step. So we basically have two parts to this model here, basically predicting what we're going to say, which is the arrow to the z, and predicting how we translate that into language, which is the second arrow. And this is going to be very convenient for lots of things. Now when we do reinforcement learning, we're basically just going to fine-tune the parameters which choose our choice of plan or latent representation, but not actually change the parameters which change how to realize this in language. This means we can do reinforcement learning, which will just kind of choose which message we want to say, but not affect how we actually say that. It's also very convenient for dialogue rollouts, so we can change our algorithm for doing rollouts somewhat. So now, I mentioned before we had this problem where basically every kind of candidate message we generate can end up being semantically the same, even for different words. We can avoid this by doing kind of hierarchical rollouts where, first of all, we just take a number of distinct choices of z. And then for each z, we're going to generate a corresponding message. And then we roll out each of these messages to the end. And because we chose different values of z for each message, for each candidate, then we could hope that each of these messages will be kind of semantically distinct from each other, and we get much more diversity in our rollouts. And this is going to help us actually come up with much more options for planning with. Okay, so to give some experiments in this part of the work, we have a couple of models. So first of all, RNN is just going to be the model I described in the first part of the talk. The hierarchical RNN is basically has a second layer which operates over messages rather than words. we got kind of this baseline clustering, which basically learns latent representations to maximize the likelihood of words in the message. And we got a full model, which uses a kind of two-step clustering approach to try and capture the meaning of messages rather than the words in the message. So measure a few things. First, we're going to measure perplexity results. So perplexity is basically the likelihood, the average likelihood of tokens in the human dialogues. And we found this correlates really well with the quality of the language the models generate. So if the models assign lots of likelihood to things people were doing, then that is a good indicator they're using good human-like language. And on this approach, we found that we got pretty big improvement for using a hierarchical RNN. And using our new approach to clustering messages, we also got comparably good results. Whereas using baseline approaches to clustering didn't really capture that. We can also look at the end-task performance. So this is dialogues against the recurrent neural net on the left and the hierarchical RNN on the right. And we see that our model, which uses our sort of semantic representations, leads to really large improvements in score over all the baselines. So it's both using language which is more like humans, but while getting higher rewards. We also experimented using this in reinforcement learning. Sorry, this graph is slightly confusing. On the x-axis, we have we show the perplexity of models. So lower perplexity is better. I should have said that before. And on the y-axis, we have the reward the model gets. So being in the top left of the graph means that you're getting high rewards whilst keeping on human-like language. And as we go right in the graph, we can see all the models can kind of learn to trade off using less human-like language while getting higher rewards. But we see the green arrow, which is our full model, is basically able to do a much better job in this trade-off. And on the left part of the graph, whereas using human-like language is getting much better rewards. And finally, we looked at using rollouts. So we've got a few approaches we're comparing here. One is kind of the baseline rollouts. One is like not using any rollouts at all. The other is using the baseline described in the first part of the talk. And finally, we've got these kind of hierarchical rollouts, which are called diverse rollouts, where by sampling distinct latent representations, we try to enforce that all the candidates we roll out have a different meaning. And again, we see that we get some nice improvements from using this technique. Yeah, finally we did a bit of analysis. We basically took 1,000 dialogues between the hierarchical RNN model and our full model. So these models get like a similar perplexity, which indicates similar overall likelihood on assigned to human dialogues. One thing we found was we made a list of very generic common messages, which we said that simple likelihood models were prone to overusing. And we find that our full model uses a lot fewer of these, so it uses less than a third as many of these overly generic messages, which is an indicator that it actually understands a bit more what's going on and is less prone to just agreeing too easily. We also found that this full model is actually a lot more creative. So for our baselines, we found that about only 20% of the things they said weren't just copies of sentences and training data. So mostly what the baseline model is doing is just learning kind of nearest neighbor approaches to situations and training data and then repeating a message they saw there. Whereas our full model actually seems to be a lot more creative. It's able to say 60% of the things it's saying are not sentences it ever saw at training time, but it was able to figure out what they should mean. It's also less repetitive. So I showed you these awful examples where the model just repeated the same demand indefinitely. And we found that our full model actually doesn't say the same thing only says the same thing more than once in about 1% of dialogues, which again improves a lot over our baseline. Okay, so to conclude, what I try to argue is to make bots can actually use language effectively, we need to make bots which aren't just trained to try and imitate what people are doing, just repeat human-like actions word by word. We need to try and get bots to actually understand the difference between what's said and what it means. And if they operate at the level of kind of more semantic level, where they're thinking about what sentences mean, they give much more coherent messages and actually give much higher quality language. I think that like the kind of main future work we'd like to go to on this is like trying to scale this up to larger domains. So rather than just training a few items, like how with bigger training sets, how much can we scale this? Cool. All right, so that's all the stuff I wanted to talk about. Thank you very much for listening. Cool. Yeah.
So I really like the idea of factoring apart, learning what you want to say and how to say it. So it seems like so at the moment both of those are being learned from the same data set, right?
Right. Yeah.
You're sort of learning English at the same time that you're learning how to negotiate.
Yeah.
But it seems like the learning English part could be done with a bigger, different data set. It's not data set or not negotiation specific. Does that make sense, or do you think there are sort of ways you could treat the speaking English as a black box and then just learn the negotiation part?
Yeah, absolutely. That's where we really like to go with this. Is like having a model where you just train a language model on the internet to be really good at sort of generating messages, and then like trying to learn to factor out what these things mean, and then use those in different situations. I think in practice, it's probably not that important on this task, just because the domain's pretty small, and learning the language you require for this domain is not that difficult. I'm not sure. Just sort of learning more and grounded language would really help there. But certainly if we want to scale up to bigger domains, then yeah, absolutely we'd want to learn English separately, and as far as possible learn the reasoning layer as something else on top of the language modeling.
So I guess when you did an analysis, was there evidence that by sampling, from the Z's, that it was actually like taking a route where it was like proposing a deal and then compromising, or was it just like completely changing its mind?
Good point. So we certainly hope to see that. Hopefully, you can imagine if you like look at the dialogue as a sequence of Z's, which is basically what is fed into this RNN. It would kind of like maybe like see patterns, like you go from this one to the next one as like that's your next compromise, and that's the next place you fall back to. Honestly, it would need a fairly optimistic interpretation of dialogue to see that. Often it seems to jump around quite a lot. Maybe it's not clear how often people are doing this either. I mean, often there's actually quite a few good solutions, or equally good solutions, and people kind of jump around a bit trying to feel out what good pattern space is. Yeah, I would love it if that happened. It's a bit unclear if it does or not there. Okay, thanks.
So what are the technical challenges with extending this setting for the agent would talk with more than two other agents? Like like you have 3 or 4 people in a negotiation. This is right now 1-to-1.
Yeah, so you imagine these agents are all talking in one dialogue, or maybe they talk to each other private? Sure, so the question is like, what's the challenges in extending this to a 3 or 4 person negotiations? So are you imagining agents like talk to each other privately, or they all share
They all
a dialogue?
share the same talk, but they are like, you're in one place and I'm with one person and I have to deal with other 3 people or 4, so how?
Yeah, so I think these settings will be like really, really interesting and like allow a lot more room for interesting tactics. So practically, it's like there are challenges like knowing like when people are talking over each other and like trying to maybe I'm just like talking to you and some other people are talking, having simultaneous conversation with some other people, and it's all interleaved together. Then disentangling the dialogue into who's talking to who would be challenging. And you'd also have challenges like trying to work out who you want to address, like do you want to address everyone or just a particular person. Yeah, I think it would add a lot of complexity to it in a good way. I think we should try and build models that could deal with that complexity. I don't have a great intuition for how well it would work, but I think it would be quite a lot harder as a task. Yeah.
Just out of curiosity, right? Because in these experiments, like all the state space of actions are actually very small because it's just like objects, finite objects that you are trading between like boards.
Mm.
I was just wondering for the general idea of negotiation, where like in reality the state space of actions are actually like kind of infinite. I'm wondering like is there any future work about like maybe getting bots to like estimate what possible actions you can even take for like negotiations? Like, do you think that is like an important like?
Oh yeah, absolutely. That'd be an important direction to go. I mean, we're kind of trying to keep it as simple as possible here, just partly because we weren't really sure if this was going to work at all. But yeah, the moment the action space gets bigger, and like to the point where you can't just easily enumerate all the actions, then a lot of this would get hard. I mean, I guess we have models for like predicting. I mean, we're kind of assuming you could easily do softmaxes over what the action would be. Maybe you could imagine doing some of the tricks people do for large softmaxes in language modeling and things. But yeah, I think the problem would actually get a lot more interesting if the space was much larger you can negotiate over and people have to like focus over particular issues. So yeah, I think it's a great suggestion. Yep.
So you said that the bots learn to be deceptive. Does this happen randomly, or is this some sort of pattern that trigger the bots that make them like deceptive? Like,
yeah.
With the reward functions, or sorry, the rewards, or?
I mean, again, it's a bit hard to like. I want to be a bit careful about the claims here because I mean, we don't want to describe too much like anthropomorphizing these bots too much. It's quite hard to know why they're doing what they're doing. Often they do stuff just because of sample from the model and they had no idea. It did seem to happen more with like kind of bots where we like the model that was just trained to maximize likelihood of human dialogue seemed to do it less than models which were trained, models which had the rollouts, which suggests that the rollouts were doing some kind of tree search, which was sort of learning that saying something like was likely to lead to good action. So if you like ask for more than you really care about, that kind of gives you this nice fallback option of like compromising, and then you're more likely to get accepted than you were in your initial offer. So I think there might be some of that going on, but it's like it's really hard to know, really.
So a lot of reinforcement learning sort of requires having a simulator, right? And some of what you're doing is you can think of it as learning a simulator, and then doing RL in the simulator, and then hoping that generalizes
Absolutely,
to the real
yeah.
world. But of course, you have this problem where the simulator doesn't actually match the real world. So one thing that has helped in like robotics is to sort of randomize a lot of different aspects of the simulator, like if physics parameters or coefficient of friction or these kinds of things. And if you can learn a policy that sort of can deal with all these different kinds of simulators, then or parameters in the simulator, then it seems to generalize better in the real world. Do you think anything like that makes sense in the context of dialogue, or is that just pretty different?
That sounds interesting. Yeah, I haven't thought about this at all. It's not super clear what you would randomize in the environment. I mean, I guess like the agent you're talking to is like something you could randomize and maybe substitute it in lots of different, have a population of other agents you're talking to, and maybe that would make it more robust to stop you like kind of overfitting to adversarial examples on a particular agent. So that sounds plausible. I should say like we don't actually have to do the reinforcement learning with other bots. We could just put this on Mechanical Turk and learn from scratch. The reason we don't do that is just because that's expensive and reinforcement learning doesn't work very well. So it would just be, I think we would probably learn best policies if we were just learning interacting with people, but it's just.
I guess it'd be nice to have knobs for like how aggressive the policy is, or.
Yeah, so I mean, you can imagine, like, yeah, you can have some kind of penalty for like how long the dialogue lasts or something, or more of a penalty for not coming to any agreement at the end. And if you, tuned around with those parameters, then you can maybe get different behaviors.
That was, you just touched on something I was curious about. If you had a, you didn't, like when you were doing results of like this, trained policy like performed better, if you didn't mention like how long they negotiated, except like qualitatively. Do you think was there like a quantitative difference between like the more successful negotiators and how, like long the negotiations took?
I don't know. I don't think we measured that. I think, unfortunately, there's a few reasons why it's going to happen. Like maybe having a long negotiation gets you a good score because you're like really stubborn and really good at like holding out for what you want.
Yeah.
Or but maybe having short negotiation correlates well because you're negotiating with someone who's just not very good at this and just gives in immediately. So it's not exactly clear how that would correlate. It probably depends a lot on like who you're negotiating with. I think we have some stats in the paper on like how long these dialogues were on average, and definitely the reinforcement learning rollouts and things definitely led to longer dialogues. But partly it was because they were just overly stubborn and aggressive, and then often this was bad because people just walked away from them without making any deals at all. So I think it's hard to say like having a long negotiation is good. I think it's a bit more subtle than that.
They didn't see, I guess, cases where someone would walk away if the negotiation went too long in the training domain, right?
Right, yeah, exactly. So that when they were negotiating with the bots, these bots were like happy to just keep on fighting with each other indefinitely. Maybe if we'd been smarter about how we set it up, we'd like given them some like. So if you give them the maximum length of dialogue, then it doesn't work because basically strategies like keep on making demands until the penultimate turn. And then the person's kind of got an ultimatum. But you can do things like have like a stochastic depth of the dialogue where one party walks where the dialogue ends and you get anything, and that would probably be the smarter thing to do, but we didn't do that. Another thing on this topic we should have done if we knew our game theory better was to iterate this. So if you have like, if you know you're going to have like 100 negotiations in the same bot, then it becomes a good tactic to actually like sort of walk away more, even if it gets you 0 points, just because it kind of establishes you as a tough negotiator and the other person can't screw you out of things. And you see these kinds of things in games like Iterated Prisoner's Dilemma, and adds a lot more complexity to the task. Yeah?
If you had data sets in different languages, would it be hard to have a bot speaking several languages?
Great question. I hadn't thought about this. I think, in principle, I think it would be okay, particularly with the kind of latent variable model I was just talking about. It'd be really cool if that model could learn like the same kind of underlying meaning across a bunch of different languages, and then it could kind of like share the reasoning steps across all languages and just change how it realizes that into different languages. I think that'd be very interesting. Yeah.
To that end, I wonder about a multimodal version of the same thing. If I used the visual modality as another language, and I could just show, like you could just do the move. And I wonder if you'd get a latent representation that was quite.
Yeah, sorry, what's the visual modality here?
Well, I just like that previous question and answer, and I was thinking maybe a way to show real grounding of negotiation would be to actually have a visual depiction.
Oh, I see. Yeah.
So I could either talk to you, or I could make a move. Cards, and then if you had an agent that could either watch the play or talk about the play, that would be even more convincing.
Yeah, that'd be super cool. Yeah, that'd be a really good way of kind of really trying to factor out what the meaning is that's in common between all these things. But yeah, we didn't think of that.
I'm also curious about sort of the same question, but to what extent does it make sense to study negotiation or develop policies for negotiation in the absence of language? So, or at least in the absence of, without English, without that constraint?
Yeah, so let's see. In the absence of language, there's actually is a ton of work on this. It goes into like bargaining in the game theory literature. There's, lots of work studying how this works. I guess what which kind?
Is it like a solved problem, or is it like?
I think like in some settings it's solved. Or there's like you can work out what optimal behaviors are, and there's like natural equilibria and stuff like that in different versions of the game. I think most of them is to get like natural equilibria. I think you have to assume you know what both people's reward functions are. But yeah, what we're really interested in is trying to combine that with natural language, which makes it a lot messier, and like all the game theory doesn't really apply so well anymore. There's also a paper now clear on doing negotiations in this emergent language stuff. Some guys in DeepMind applied it to basically this task, and they have a nice paper in iClear.
Any last questions? All right, shall we thank our speaker again?